All right. I guess we can wait for a few minutes and then start. If you have any questions, you can ask in the meantime. And yeah, and then we can start. Yeah, that's a difficult question to answer. It depends. Um, if you're just starting out, basics of just if and for loops are fine. I mean, you can pretty much write everything from it. Some functions, knowledge of recursions, that's very basic. But if you're going to uh, do it as professionally, then yeah, we need to learn much more concepts. So if you're specifically working with a specific language, then yeah, you have to put up more effort and learn all those concepts. If it's for, let's say, research and where the focus is more on, like, let's say, computational sciences, where the focus is more on the sciences part, but with some added flavor of um, computing. Okay. So there, I would say maybe just knowing the basics and foundations of the language there. Let's say the code is written for that field of computational sciences, the code is written in Fortran or maybe C++. So knowing those two, that specific language, I guess, is enough. So yeah, that's what it is. If your research is actually in developing hardware or actually writing low-level software, designing compilers or something like that, so then you have to go way deep beyond. So that's some perspectives I can give you. Yeah. For quantum computing, there are actually a lot of languages. The most, I guess, currently the most popular is Qiskit by IBM. You can also look at the one by Google. Um, I think Microsoft also has its own language. Honestly, they're pretty much um, not that different because in itself, quantum computing is just an like it's an idea of linear algebra in a way. So the idea is to offload some certain parts of the code to quantum computers. So um, yeah, those languages are not very how to put it. It's not the language that's the difficulty there. It's easy to grasp. It's easy to pick up. The difficulty, in a way, if one has to specify, then it comes from the actual paradigm itself. So quantum computing works a little differently than classical computing that we are used to. So there you have to actually focus more on the math and how the computing itself happens than worry about the language. The language is not that hard to learn also. So yeah. Um, I don't know about that. I mean, Yeah, I guess if you want to learn everything, then it might seem daunting, but you can take it uh, step by step. Maybe first learn programming, then if you're interested, learn specific language. So like let's say C++. That's what we are doing. Python also, if you're interested. Things like that. If you're interested, you can learn for Fortran also. Nothing stops you. Um, the focus I feel should be uh, if you're learning a language, try applying it to some problem. So that's actually how you actually learn. It shows you how the language actually works. So like last week we were discussing lambda functions. So writing code and writing examples like this actually drives home the message. Um, so yeah, things need to be taken step by step. That's what I would say. It's not uh, easy, yes, because honestly, if one thinks about it, there are a lot of things coming together to make something work. Then of course, these things have not been they have been in development for a very long time. A lot of people have worked on it. So yeah, understanding every piece of it will take time. This is honestly true for everything, not just C++ or its modern features or in quantum computing. Okay, all right. So I guess we can just recap what we covered last week. So sorry, it was just yesterday. My bad. But nonetheless, last class we discussed lambda expressions. So first we see an example, okay, where we define a constant integer m, set it to 10. So the idea is that we want to calculate remainder when a given number that we pass or we want to calculate its remainder. The divisor we sort of want to keep it fixed. That's sort of the idea. Okay. So let's see how different ways we can do the same. So the first way is to have a function. Here we define a global variable constant integer. Okay. M, set it to 10. Okay. Now M is going to be the divisor and it's not going to change. Okay. So this function then returns the remainder when divided by M and also takes the input n. Okay. All right. Then you can just print cout remainder for call the function and then we want the remainder for 15. So this prints the actual output. All like so this is fine. All good so far. The second way to achieve the same thing is using a struct. Okay. Have an internal private member m. Okay. So when we actually construct this struct, pass 10 to it. So then what happens is it sets, so this is the constructor for the struct. So it sets m as underscore m, which is what we're passing 10. So this for this specific object of this struct, okay, this instance, the value of m is 10 for this instance. And sort of it's constant because it's private and we don't have access to it, so we can't really change it. So in that sense, the divisor also doesn't change. Okay. And when you access the function, which is this operator small brackets, okay, so we have written this function inside the struct so that when we have this function, when we have the object, we call the object like a function. Okay. So we call rem and then put these two brackets. Okay. So because of these two brackets, okay, so it calls this function, takes the input n and returns the remainder. All right. So now this is what I want you to also observe. Keep in mind the way we are trying to achieve the remainder, okay, is something which looks like a function, takes the input to whatever we want to divide, okay, and then returns the remainder, the actual answer that we see. Similarly, very similar to that happens here also. Here, don't get confused. Here, because of how the object gets created, because of that, we have to write it this way, like have to pass 10 here. But when you repeat the same thing again, here we're not creating so here it's the creation or the instantiation of the object, okay? We're actually like creating that object. But here it is actually calling the function. Okay. This also works as expected. It returns n percentage m, okay, or the remainder when n is divided by m. So very similar to that, you can replace struct with a class. Okay, pretty much everything remains the same. Here you don't have to just write struct. You can use the remainder, the class name, and construct the object. Okay, so this is sort of the idea behind using struct or classes or just plain old functions. And when you use class, okay, to do something similar to this, it's actually called a functor. So you see more examples here. A functor is essentially a class which behaves like a function. So if you see here, we defined a class itself. I name it as functor. Okay. So I define func, func, the object for that class or of that functor. So func is a functor now. And if you see here, after it is defined, okay, it only has certain ways to call its functions. So here the defined function with these two small brackets essentially implies that func when taken 5 will return this body. This addition, it adds 5 to it. Now here also the func looks like a function. It's an object, yes. It behaves like a function. Again, a functor. Normally functions take small brackets like this. Okay. We can also have a definition with square brackets, but again, that is usually reserved for places like for dereferencing, example in standard vectors. Okay, but you can also do this. Okay, the other idea is with a functor, you can have, let's say, different functions. Okay, like different functions defined like this. So it itself behaves like a function. It can also, maybe you can, if you want, you can have this also, or it can itself carry a function like, let's say, increment, and then you can call that function itself. Okay. All right. So that sort of covers it. Then we see the actual, the other way, lambda expressions or lambda functions. Now, we can do all this same with lambda expressions, which we also saw last week, we saw last class. So before that, what's lambda function or how is it defined syntax? Essentially, this is the syntax. There's a capture list. So first of all, you start with square brackets and then a parameter list with small brackets. Oh yeah, I'll start. I'll just quickly cover this and then start pointers. Yeah. And yeah, so we have a parameter list, okay, which takes a set of parameters. The lambda function takes it, and then a body. Very similar to that, you can just take an example with no capture list or no parameter list, just with a plain old body. Remember, this line has a body and it stores this lambda expression inside print. Auto is very useful here. We don't have to worry what it's returning. We can just define our lambda function here. To call the lambda function, you have to use small brackets. Okay. And then you can call this function as many times as you want. If you have the whole lambda function and then use brackets, then the function gets called here itself. Okay. Instance of it just once, and then that's it. But if you want to use it repeatedly, you can put it inside some variable, okay, and then call that variable itself. Okay. So that variable sort of is the function that, right? What we're saying. To call the function, you use this same old small brackets. So that variable sort of works like a function. So hence lambda expression are also functions. Okay. Then we took some example to how to use parameters. So if you have parameters, then your lambda expression expects parameters. Okay. Similar to that, you can have a auto clause and define your lambda expression. When you call that function, you have to pass parameters as many as it expects. Okay. Then we saw after the parameter list, now the capture list. Important thing to note, capture list captures the value. Let's say here it captures the value itself. Then you have to understand that once it captures the value, it stays the same for the lambda expression. Okay. Then as many times as you call, you can technically not change the capture. Here, because I've passed by value, okay, so M doesn't change, and you can, and it's immutable also. You can't change it inside the body. Okay, so we can do also something like this, pass 15, and it does the same thing. Okay, all right. I mean, as in at least it behaves the same way. You can give whatever input you want. Here, okay, here it will be the same. M is set to 10 here. Okay, in this case, but M is set to 5, so it will actually return a different answer. All right. Because this is the instance this lambda expression gets captured, and this is an instance where this lambda expression captures M. Okay. But once it captures, for every other instance you call remainder and pass 15 to it, it will always return the remainder with the captured M, which is 10. Okay. But here, in this case, here I've reset M to be 5. So when this gets captured, M is 5, so you'll get a different result. So you'll get 0. The remainder will be 0. Okay. The second way to capture is using reference. Again, because it's a reference, it is not immutable anymore, it's mutable. So you can actually change the value. So this is allowed. And the important thing is the many times you call it, each time it changes the value and keeps a track of it. Okay. Because you actually pass the value by reference, pass the variable, okay, by reference to the capture list. Now it's in the scope of main, so you can actually print 10 to keep track of how the values change. All right. And then, yeah. So here we take an example where we pass both captures, as in a capture by value and a capture by reference, two parameters in the input, and then a body which prints whatever values all these values it's taken. Essentially, that's it. Here, then we say we set the value to 0, set the reference, fine. Here, the value gets captured. Okay, so it sets so it actually, when this check is this lambda expression is actually called, it's actually set. Okay, so it's the value, so which is 0, and this value val is set to 0 for all the instances of check. But reference is taken as a reference, so we need not actually set it here. When we actually call it, it affects the body actually, right? So when we actually call it, so here's the first time I call check. Before that also, I have the option to set ref. Taking all these examples, where we change ref, change val, change ref, and call check with these parameters, we can try to see how the behavior of val ref parameters 1 and 2 change. Okay, how it affects the lambda expression itself. All right, we saw that also last class. And then the final thing, um, so yeah, exactly. One last thing, maybe I did not mention it, but this is essentially how we write the same lambda expression. Sorry, the same remainder function what we saw before. Okay, with all these instances using struct, using function, and everything. This is the one where this is how you write the same thing using lambda expressions. Okay, behaves exactly the same way. There's a function named remainder, takes value as n, and returns the actual remainder. Nice thing. M stays constant because it captures the value, and that's how remainder function can be made into a, or like a expression. You don't have to actually write a separate function or anything. You can have it through a function like a remainder here, and which goes out of scope once your function ends. Yeah, it's main, but well, anyway, I think you get the idea. Okay, so here we see a lambda expression to do a code. Same code. Essentially, you have to write something like this using struct, which has more lines. Okay. While lambda expression, you can just write the same thing in a single line. Here also, I've set val to 0. I've defined ref. I've defined something called a check function. Okay. And then sort of, okay, this is you can think like a function because I've overloaded the operator. So it's actually check is a, how do you put it? Check underscore f is the actual struct. Okay. We're setting it to check so that it can actually take values now. Correct. Something like this. So yeah, behaves like a function, takes inputs, and so on. So the same thing as what we're trying to do here. also is happening here. And the important thing is that this is achieved using lambda expressions. And conversely, we started with functions and then went into structs or classes to do the same thing, right? So we saw how to do it with lambda expression. You can do the same thing with structs. Same code, same idea. You define an integer val, private, reference, again private, that's fine, but as a reference, then you set these values, okay, using the constructor. And then after that, using operator, uh, is defining the operator small brackets, you print the values. Okay. Gives you the same output as before, but you now done using structs. All right. That's more or less the recap of lambda expressions. If you guys have any questions, feel free to ask on this topic. Yeah, let's start smart pointers now. Okay. Okay, just give me a second. And that's as usual, we want to print stuff. So IOString, main function, then yes. So now we'll start looking at an example where I won't run this code, but to give an idea, you might remember we created some classes before, right? Something like class, my class. Okay. There is a, just for now, I'm not filling it or anything. Just think of it like there's a class which exists, okay? And it has a lot of stuff in it. Now we create generally the class is as this, okay, an object. Class name, the object, okay. If it takes some parameters, so then it takes some parameters, okay. So let's say parameter one, parameter two, or whatever. Okay, all this. I'll more or less write it in a pseudocode fashion to, I guess, the um, drive home the idea. Okay. The other way to do the same thing to define this object is, yeah, sorry, yeah. Take the class name, but instead of defining the object, we define a pointer of that object. Okay, so object, I'll call it PTR, object pointer. To actually define this, what one can do is use the new keyword. New is like allocating memory. It's similar to malloc in C, but C++ has its own um, keyword for this, which is the new. New is essentially, and then I'll put my class. Okay. Let's not worry about parameters for now. Okay. So just imagine that this object is getting created. To create this pointer, you do new of the class, store the return of this. So basically what happens is it creates the class object. Okay. It creates an object of the class and it returns a pointer to that class. Again, very important. This is not like starting position of some array or anything. Think of it like there is a way in which there's some memory allocation which happens to the class itself. Don't worry about stack instantiation, but essentially think of it like there is a way to there's a memory to which the object belonging to this class has been allocated. Okay, and there is a pointer where we sort of know where it starts. Okay, that pointer is stored here in this object pointer. Using this data type as in my class pointer, we can actually access now the class is the object and its members and everything through this pointer. Essentially, that's the idea. Yeah, the way you instantiate in, I guess, Java and C# also the same, because this is also very common. Instead of just defining the object, okay, you define the pointer to the object. The reason sometimes to do this is it's easier to pass around pointers than the object, because then for object you have to pass by reference. Sometimes you don't want to do that. There can be multiple reasons. Okay. All right. So this is my class. Okay, done. So what I am getting at is this sort of creates an ownership. So, right. As in, now object pointer has an ownership to the object. So this is a pointer and has an address pointing to some sort of object created through new keyword. Okay. Now let's say I set object to as null. Then what happens is it now this object, it's called it pointer, not object pointer itself. Okay. This I'll just comment for now. Loses ownership. So if you accidentally overwrite the pointer, then the actual allocation to the object is there somewhere in memory. Okay. But the only uh, variable or only thing in the code which had any idea about that object was this pointer pointing to it. Now, if you set that itself to null or something else, then nobody has any idea about that. Why star? Which one? Oh, this one. This one is a pointer. So that's what I've been saying. This one is not an object. So new class, new of anything, returns a pointer to that object. So class is my class is the class of which sort of a blueprint of which we want to create an instant or instance of an object. We don't worry about the object itself, but the address of starting of that address in a way. And think of it like in air quotes. Now, the pointer which stores that address is this guy. It's very similar to integer pointer or double pointer or anything. It's the custom class pointer, okay, which stores this pointer to that object. And to access that object, we have to use now only way to do that is using object pointer. Okay. In a way, yeah. I wouldn't say it's more control. It's just another way of doing the same thing. There are various reasons one people just don't create object, but pointer to an object. Okay. You can, I mean, it really depends on the use cases, but nonetheless, there's something you can do. The point is, if you set the pointer to null, then now in your code, you actually allocated the memory and now nobody's pointing to it. So, and you lost the address to it also. So this is very bad. And this is something, an example of memory leak in assignment. Assignment, yeah. Yeah. So you can have, yeah, one has to be careful while assigning. You can have memory leaks. It's a memory leak because you actually uh, allocated memory, but now nobody is pointing to it, so it's just there. Okay, which is not good. You can't point to null in traditional way. You can just define a pointer and just start with null. You can do it. It's like nothing stops you. But the problem is, and storing null to pointers is not like a bad thing, but it's a bad thing if it's actually pointing to some allocated object. Okay, right. Let's take another example. So we'll have the my class. Sorry. This time, uh, pointer a. Now I'll call it again new my class. So one has to be careful. Here it creates an instance of an object new and passes and returns a pointer to it, which is stored in object pointer. Here also it does the same thing. It creates an instance of my class, like an object, okay, passes the pointer to it and stores a name. These two need not be the same thing. Whenever you call new, it creates a new object every time. Okay. So again, this also creates ownership. Okay. Right. And then let's say I have the my class itself pointer. Okay. This time I'll call it as a B and then A. So like store A to it. Yeah, I'll format this a bit better. Whatever it takes. Okay. So A is a pointer or data type my class pointer. My class B pointer is also a pointer. Now when I copy this, it copies the pointer itself. Okay. All right. So this is a ownership. Okay. But copy. Yeah. Yeah, kind of. Yes. Because B is also storing the pointer to that object. So A stores the pointer to that object and B also stores a pointer to that object. Yes, it will. Because they're pointing, actually, technically speaking, it's the same object both of them are pointing to. Okay. Now here's another thing you can, I mean, one has to be careful. If B was already storing some object, if you do this, okay, and let's say instead of B, it's object pointer, then you're overwrite. Okay, and forget that I don't define it. Okay. Then you're overwriting with a new object. Okay, as in not new object, you're overwriting the pointer, you're storing another address to it. So again, object pointer is the actual object it was pointing to goes dangling. So it is not pointing to that anymore. You know, idea if B was pointing to something else, overwriting one has to be careful. So you can actually create errors with copy. So as I would write it as error with copy. You can have problems, okay, while copying also. Overwriting should not cause any error, as far as I understand, because it's just a pointer. So yeah. The other idea is, so this is what we saw now. The other error that you can have is, let's say you delete B and then try to delete A. Sorry. Normally that's what you do, right? Like, so this is one example. Okay. Then another example that we're trying to see where uh, you could have this also. Instead of null, you store A. That's also uses ownership. Okay. Now let's focus on this one now, like the complexity with it. All right. So B has the pointer. A also has a pointer, like the same pointer, pointing to the same object. As in same pointer, when I say they have the same address to the same object. Okay. Now, since they're pointers and we use new to create them, we can also use delete to delete them, as in deallocate the memory and all that. So don't worry about how the deallocation happens. It's taken care of by the command. But the point is, the object that was being pointed to by B gets destroyed when delete B is called. Okay. Now imagine because an object is deleted and you call delete A again, where B was storing the address to the object, like the same object, right? So let's call that object obj itself. Just imagine. Now you're trying to delete that through A also. Yes, exactly. Then you'll get an error. This is with the problem with uh, having the same uh, object being pointed to by many pointers. Okay, so this is a source of error. All right. So I hope you appreciate this kind of errors. Now, that's essentially what smart pointers will automatically take care of for you. Oh, fine. Okay. So before appreciating how smart pointers are important or what they do, you have to understand what kind of errors can happen when you're dealing with pointers. Okay. So something like this is an example. Okay, this question. There's no particular reason, but the problem is, let's say you don't remember or you make a mistake or something like that happens, where you forget that you are actually storing the same object in both A and B. Let's say the code is very complicated. A lot of variables have been passed around, pointers have been passed around, a lot of things happen. Just so happens that at one place, multiple pointers are pointing to the same place, same object. And one of those pointers was deleted first, which that will not throw an error. It will work because it was pointing to an object. You ask it to delete it, deleted it. The problem comes when you try to delete, like this second line, some other pointer where it points to the same object. Okay. There's actually no reason uh, A- B is done first and then A. There's no real order to it. The point is that one of them is done first and the second one is done again. Like there is out of these two pointers, I delete one first and delete the other one next. That is the point here. There's absolutely no reason you can do this. Okay. You can absolutely do this. Then this line will throw an error. Okay. All right. So deleting B deletes the object pointed by B. Okay. This also removes ownership. And deleting again. Okay. Is also called as double deletion. Again, throws an error. Okay. So one way to solve this, okay, is again, you probably can't run this code, okay, but more or less the syntax should be clear, okay, because I've not created any class or object. Okay, I guess this should work. Let's try it. This be fine. This should be fine. Things should be fine. Things should be okay. Okay. Right. So let's define and run. Yeah, everything is fine. It works. It's an empty class, so I thought that should be okay. Yeah, as usual, it is fine. This is fine. This is fine. And this is a source of error. Okay. And this is also a source of error. And this is also a source of error. So let's see if it throws an error. Yeah, it it will compile and run. But now the problem is you have dangling pointers. Again, like you can see, sometimes these errors don't actually come up unless they actually try to when you try to access memory out, so which is not accessible, right? So whatever this object was pointing to, I don't have any access to it. It's just there in the memory and my program ends. So the problem is your program doesn't have access to memory and all. So this is not a good practice to do things like this. So again, and if you see here, it running the code also did not throw any indication that something like this happened. Okay, that's what I want you to appreciate, because it did not throw any indication that something like this happened. It sort of becomes very important to actually handle this as we go. Okay, with I will say with smart pointers especially, there is a solution as present now, and something like this is what becomes very important. Okay, so because like you see, runtime doesn't say that such error crept into our code. Okay, so let's say we try to delete it. and then run. Okay, good. At least it threw an error that we try to double free some object which is already deleted. Okay, good. At least that happened. So managing memory of through pointers becomes like very, very important. One has to be very careful. All right, because not all the time you'll get errors like this. So one possible solution to that is I think question. One more line after 21. Uh, Again, also, yeah. I mean, if you have another object pointing to it, you will get an error. Yeah. And as we saw, if I uncomment this line and then run, you get the double deletion error. All right. So I'll present a solution to this. Define a function. Okay. Have the my class pointer. Okay. A. Let's say call it 0. So it's like default, it's set to 0, or you can think like it's set to some default value. Now we can actually do it exception handling. So try a equals to, so this is some initialization. You can ignore the zeros also. Absolutely okay. You can just define a and b because we're going to set them to some values now anyway. So new my class. Okay, with my class new done operator with like used with my class returns a pointer of object. We stored that in a. Okay, awesome. So if you point b to null, with will a also become null? No, it doesn't. Think about it. A is a pointer, B is a pointer. A already stores an address. If you set B to null, A still has that address. Okay. So actually, if you think about it, you can do this. This is double deletion, right? So we'll delete B. Okay. Let's say set A to null and then delete A. I will comment this for now. This is not thrown error because A and B both were storing the same address. Okay. Now I set A to null. Delete B first. So whatever object B was pointing to goes away. That gets deleted. Now, because A is pointing to nothing, deleting A is fine. Okay, so this is not a double deletion anymore. Okay. We are just comment this for now. Okay. Then object pointer A null. Yeah. Then this is basically the same example that we saw before, but this with this line you will not it will not throw an error. With this line, this delete B will throw a double deletion error. Okay, I hope that is clear. That's the thing. Forget about setting null. So if I take this example where some object was created, stored into A, the same pointer is now stored into B. I delete B, so that object is gone. Now A has the same pointer to that object, but that object doesn't exist anymore. So if I try to delete, then it throws an error. No. Existence of B is not dependent on it. As in the pointer, the object they are both pointing to is dependent on each other. So because I deleted B, I don't delete just the pointer. I delete the object itself it is pointing to. Okay, very important. I don't delete the pointer only. Okay, I delete the object it is pointing to. So B deletes object obj. A also is pointing to the same object obj. Now because it is already deleted, you can't delete it again. That's the main idea. But if you set A to null, it is it's not pointing to object anymore or obj anymore, which is okay because B is still pointing to it. And if I delete B, I delete the object also. That is fine. And if I delete A, which is also fine because now A has just null. Okay. Right. Now let's do this. Where we write a try and catch, like exception handling basically. where A is A now has a pointer. We use the new keyword with my class. So it returns instantiates an object of my class. It returns an object, it returns a pointer to some object, and we now store it in A. So far, so good. And let's say uh, I have a function called function. Okay. It does nothing. It's just a void function, takes nothing. Body is also empty. Okay, that's fine. So I have to make it public. I want to call it outside the class. All right. So now I'll call that function. Okay. Remember the arrow operation because A is a pointer, and to call its member function, okay, you have to use the arrow operation. So arrow operation is basically dereference. So dereference the pointer, which means we access the object. Then we use the dot to actually access the function. So arrow is basically the dereference plus the dot, both together. And function doesn't take any input, so that is also okay. That's absolutely fine. Anyway, it's basically an empty function. This all is just to show the idea behind all this, how things work. Okay. All right. I guess that happened. In any case, uh, let's say we we generate we create an object, call some function, and then the work is done. Okay. We can do something similar. We create V very similarly. Okay. New my class. Done. Then all the function. Okay. That's it. More or less the same idea. We create an object, store it in A, create another object, store it in B, call it their corresponding functions. Here we won't do anything, but imagine that there was some code where it does some task. Okay. Now this is fine. What we can then do is, if this one doesn't work, then we can actually catch it. Okay. So there's some kind of catch that happens. Okay. If it fails, then we delete it. Delete A, delete B. And this so and okay. After that, just for safety, you can just delete it. Because we created the pointers. Now we're just not deleting them. Okay. And then return. That's all. So with some exception handling, you can handle all the worriness about if this got deleted or is this not set or whatever, right? You can have exception handling everything. So this is one way of handling pointers and memory management in C++ at least. You can pretty much do the same thing in C also. Instead of new and delete, there will be um, malloc and I think free. Yeah, in C. This is better code, yes, rather than just worrying about when things later, but it becomes a little cumbersome, right? Right. Writing try and catch expressions every time for all cases, right? So that's exactly where smart pointers come in. Okay. Right. All right. Where they actually take care of a lot of the heavy lifting for you. Okay. So this is the first one. This is safe. Yes, this is absolutely safe. Requires a little manual intervention of writing code, but absolutely this is safe. This is sort of a like a blueprint of what like what one can do. Like put it in basically under try and accept. Okay, this code might not work. I'm not sure of the syntax, but this is sort of like you can take it like a pseudocode. You can run it and see might work. Yeah, it throws some at it. Anyway, yeah, okay, that's fine. I'll just comment this or as a solution. Okay, but the main idea is that you can put whatever you are trying to do, okay, if it's deleted and all, you can't access the function anymore. So those kind of errors get catched. If you can catch them with the try and catch, then you can just delete them. Okay. Now let's look at how to smartly do the same thing using smart pointers. So there are two principles on which smart pointers work. One is RAI, which is resource, I think acquisition, yes, acquisition. Spelling is fine, I think. Acquisition, yes. Is initialization. Correct. And then the second concept, RA, RRID. First is RAI, resource acquisition is initialization. Then RRID, where resource release is described. Basically, it tells when to construct an object and when to destroy an object. That's all. And it might seem very simple, but it's an extremely powerful concept and makes heavy use of scope of which is there in C++. Okay, let's see with some examples. Okay. These two basic ideas is essentially behind all the things that smart pointers do. It's called a class, which is a smart pointer. Okay. So first of all, public. Smart pointer. Let's say it takes some data type and pointer. Okay. Find a private number called pointer. The pointer. I define a variable, okay, member variable, which is of data type T. So that is some I can put it like a type name. Yeah. So there's some template T. We have pointers. That is the data type of the pointer. Okay, it takes underscore pointer, sets ATR to underscore pointer. Like takes underscore pointer, sets it to ATR. Okay, that's fine. Some body, which I don't need to worry. Yes. All right. Then and the function. Now, this is the constructor that I've written for the smart pointer class. So this is essentially RAI or uh, resource acquisition is initialization. So what happens is when we call this class smart pointer and instantiate some object, it takes some pointer, sets it to the internal member. So that is the resource is the underscore pointer, which is acquisition, like its acquisition happens, okay, and then initialization happens. So initialization is setting it to some private member. Okay, so this is RAI. Now, what I do is smart pointer ampersand operator equal to, and then this. So this is the equal to operator being defined. Okay, let's say it's cons same smart pointer as reference, and then something called other. There is some acquisition that happens. As in, this function is defined this way. Okay. Some we don't care what the body is. That's fine. This is again just an idea how the class will look like to make you understand how smart pointers work. Okay, we don't really need to go into how the nitty-gritty of the body looks like in each of these functions. Then we write a destructor, smart pointers, okay, which doesn't need to take anything. You don't need to worry about it actually taking anything. And then delete the same PTR. All right. Comment this. Now, this part is uh, RID. Resource release is destruction. As in, when the destructor of that smart pointer gets called, so this is the destructor. In the body itself, we have the deletion for the pointer. Line 12. Oh yeah, line 12, I'll come to that. It is essentially equal to operator that is defined. So remember, we defined small bracket operators like this using the keyword operator. Here the equal to operator is defined. That's it. It takes some object with like equal to and then sets it. It does nothing, but again, it's just some function that is written for completion. Currently, it doesn't do anything. What I wanted to focus on is, yeah, syntax was for the small operator. This for equal to. So this then makes sure that the smart pointer classes object has a function, has a definition for equal to. So if you do this, then it has a definition for these brackets, okay, which makes it like a function. Now you have to use equal to it. We'll see an example. If at all I use it. I don't think I use it. Uh, and nonetheless, you can ignore this. It's not required. We can also define some more functions, okay, like this. I'll define operator this, okay, which is a const operator with the body uh, something, let's say, or with some body, let's say, okay, return the pointer itself. So this sort of gives you a no, sorry, not yet. This sort of gives you a way to access the internal member, the pointer itself, the raw pointer of the smart pointer. I can also make a reference, okay, using the operator ampersand this, and or it may not be const, I think. Or okay, then let's make it const. The somebody then return the dereference, okay, to that pointer. This is essentially what I'm doing is using the pointer, I give it some more functionality. If I use the arrow, okay, it gets the actual pointer. I use the ampersand reference, it actually gets the dereference of the object, as in this actual object itself. Okay. See the private number and everything. Okay. Now let's see the actual pointer in action. So take my smart pointer. And let's say the data type is the same as my class. Yeah, it may not be type, it put class or something. Okay. And then I call it smart pointer SP, which takes input. Okay. It takes input some pointer, right? So here itself, I can make my new class. I can just do new class, which returns a pointer. Okay. I'll append, yes, which returns a pointer and then passes to the object SP, which is of data type smart pointer templatized with my class itself. Okay. The same my class. This is the one. So the underscore pointer is basically the pointer returned by new class. SP is the object of smart pointer, and it captures the pointer, sets it to its internal member variable using RAI. Okay. And then I can access, let's say, some um, function. I haven't defined it, but well, oh no, actually I did. So the function is defined here, right? So I can use SP now to access the function defined in my class. So I did define my class, yes. Inside my class, I had defined function. Now I can access that function using SP because I've defined arrow operator as this, okay, which is basically returning that pointer. And then that pointer, the pointers function is what I'm trying to access. Okay, this is all good. Now, if you think about it, within this scope, SP exists. And when SP goes out of scope here, smart pointers destructor gets called, which deletes the pointer, which is basically the pointers pointing to the object returned by my class with new. So this is a very smart way, and you can actually delete the actual object, right? So this is what a smart pointer is. Yeah, a very simple concept of scope and two ideas, RAI and RRID. You can really easily, very easily manage memory. While yes, C and C++ are notoriously infamous for memory seg faults and seg faults, memory management, memory leaks, so on, like so many things you'll be hearing from many sides. Honestly, if you think about it, using something like this smart pointer itself, like if you write a basic class, yeah, I mean, you can take care of the whole thing all together. I mean, it's just automatic. You write the code once, wrap it around some smart pointer class. So that's what essentially you're doing it. If you think this is easy, see, I'll show you something else next. Imagine this is provided to you in a standard, just a function. So that's the beauty about smart pointers. It's available in a template, as in it's available in the STL library, the standard template library itself. Here we have written it manually to understand the concept. It's actually just given to you. So I don't know if we have examples for that. I think we do. Oh, yes, we do. Okay. Yeah. I'll discuss some example of that. So yeah, it's as simple as that. And the best part is you don't have to manage anything yourself. It automatically happens. So the key idea is you wrap your pointer around a object. While the object gets created, RAI happens, as in when the resource gets acquired, as in acquisition happens, initialization happens. Okay. And when the resource, the actual object gets destroyed, it gets deleted. The pointer it was holding gets deleted. Its destructor just deletes the pointer. Okay. All right. Now let's look at another example. Include the IO stream. We also need another header file, which uh, will include something called memory. I'll show you why I included this file. Okay. So yeah, so let's say there is a struct called foo. In a way, yes. In a way, yes. So that's the nice thing about smart pointer, as in the idea is this: create a wrapper class for your pointers, which automatically deletes it when the object goes out of scope. Yeah, you can do it manually, but sometimes your code gets very complicated. So there is a very smarter way to write this also, as in STL itself provides it. So we'll see that now. But yeah, you can absolutely do this, or you can keep writing, try and catch lines. You can do that. But I think this is much, much simpler and write it class. There's even a better way, which what I recommend to use. So we should see that now. So the foo. Okay. Yeah, that's actually true. A lot of times you actually learn better if you write that code, and sometimes you want more control over how the smart pointer should work. So absolutely, you can go with the class itself. Yeah. Then the constructor just prints that foo, meaning it was created. And behind, okay, that's it. As in it was constructed. I'll make the destructor also pretty much similar. Okay, with the squiggly line operator. Okay, uh, essentially mean that this is the destructor and the destructor was called. Here it means the constructor was called. Essentially that. That's it. That's all my. That's what all I want from my struct. Write a function called bar. Okay, which has which basically puts the output as this. So this is a function inside foo. So and bar is called. So that's it. Foo bar and then envl. Okay, awesome. That's it. We'll also define a function that takes const and then like foo with reference. Okay, so it takes an instance of that uh, object of that struct foo. Okay, this is list. And then as out and uh, const foo plus such, just to say that it was called. That's it. We don't really worry about what the body does. Essentially, we want to know when it was called. So that print statement essentially keeps track of that. Okay, this is done. Then we write the main function. Now this time, uh, instead of using a class to wrap and everything, I'll just do this. The standard tuple library itself has a way to do what we just did using the class and everything. So you make a unique pointer. Okay, sorry, that's actually pretty. That's it. The standard unique pointer is a defined class which takes the data type of whatever thing you want to make it with. So here we passed smart pointer template, right? My class. Think of the same thing, but in STL. So it takes foo, okay, creates the pointer T, okay, and call it PTR. Why not? Or maybe smart PTR. I'll call it as PTR. And then to make it, you have to use something called make unique point. No required. Make unique and then take the template, which takes the template foo, okay, and then call the function. So this is fine. To be clear, so this is from C++ 14 syntax, where the SPTR now owns foo. Okay, there's another syntax you can also follow, which is a little older syntax. Standard unique pointer. Did I write that correct? Yes, I wrote that correct. Takes foo, and then we can do just pass not with p SPTR and pass new foo and then yeah. So this is in from C++ 11. As in this is you can do this in modern C++14, 17 or whatever, and 23 and everywhere. But this starts from C++11. There is another functionality which you can also do in from C++14, which is there is a function called standard make unique, which makes a unique pointer of foo, okay, and then returns that to equal to like left of equal to as an S pointer. Its data type is standard unique pointer. Means it is a unique pointer. I'll talk about what unique and shed pointers are, but essentially the idea is that this is a smart pointer which keeps an instance of some object of data type foo, okay, in a pointer SPTR. It has all the nice functionalities of smart pointer. As soon as this SPTR goes out of scope, that object gets deleted. And that's it. You can write the do the same thing with this syntax that we saw before using new. Okay, you can do that, or you can use standard make unique. That's it. That's the only difference between these two lines. Okay. Here, SPTR owns O2. Okay. Yeah, so standard unique beta is defined in IOStream, right? No, it is actually, I think, included in the default header libraries. You can look at, I'll take a look which header library it is there. But as far as I understand, it's, I think in some, whichever header library it's included, it's by default included while you compile. Let's say with GCC or something. So I'll check it. I don't actually remember what header file it has. Yeah, it's defined in memory itself. Yeah, that's fine. Yeah, just wanted to confirm. Yeah, it's defined in memory itself. Yeah. Do you have any additional advantage? Yes, you don't have to make this class. I did all of this using a single line. So this is a smart pointer. So what you see here using the class smart pointer is basically a sort of a bare bones implementation of standard unique pointer. Okay. No, we did, yes, but we have to make this class. It just so happens that this class is already defined inside standard apply library. Here we have to actually make the class. Yeah. Because it's so important. I mean, one can obviously, I'm not denying it. You can make this class and manage it yourself. Yes, I completely agree. But it just so happens that STL, okay, memory header file already includes this. So you might as well use it. Okay. Right. So next, so if smart pointer, then you can do S smart pointers, but as in if standard pointer is still pointing to something and is it, let's say it's not null, you can call the bar function it owns. Okay. So S pointer is basically pointing to foo, right? So think of it like a foo pointer now. Standard unique pointer with class template foo. So it's, you can think of it like a S pointer is foo pointer now. So um, I'll make a note. Foo pointer S PTR. You can think of it this way. So to access a member function, you use arrow operation and then the function bar, which is with brackets. That's it. Basically, this if statement takes care of that. All right. Okay. essentially it is, if it's not pointing to null, then we should be able to access it. That's what I'm trying to say. Another thing one can do is this. So don't get confused. Here is just some scope that I've started, and I'll write the code. So all the code is inside this scope. Here it won't point to null, yes. But this check sort of, it's not relevant to this part of the code, but you can use it other places. I just wanted to show you guys. You can check if the point is not null and then call it so that you don't actually um, face errors. It's just a one thing you can do, just so you know. Then what we will do is make a standard unique pointer again of foo. Okay. Now this time Q is the stand pointer. Okay. So S was the SPTR was smart pointer. Okay. Q is some other pointer that used as an constructed using standard move on P. So what this does is it moves that pointer from P to Q. So essentially S beta was S pointer, okay, was pointing to foo. Maybe I'll make it to PTR. Now Q PTR owns some object of foo. Okay. Now I can call, there's a function, okay, which takes an object reference of foo. Okay. So what I can then do is dereference to PTR. Okay, and then call that function. You can do that. And then I can set S PTR as standard move. I can again move back to P. Maybe this will be too much. I will start commenting and then showing the code, but let's just complete for sake of it. Yeah. Uh, yes. Now we have a cout. Says destroying because remember QPTR goes out of scope outside this. Okay. And then and like yeah. So the question is what is this curly braces 23, right? So this is just a scope. The nice thing about scope is you can start and end in any part of the code. So if I didn't have this, the scope of this portion of the code was from here to here. Okay. I can just actually put some scope like this also. This is absolutely valid. It's not like this is a part of a function's body or anything. It need not be. Okay. You can have scope in itself contained. That's fine. So then we will do something like this. Essentially what we did here, but now here. Okay. Now let's look at each other instance carefully. Yeah, it is just a scope. So we discussed that RAII and RRID both, okay, work when resource is initialized or destroyed. And for any object in C++, destruction happens when it goes out of scope. To reflect that itself, I've written the code so that I've given Q pointer its own scope. Okay, Q pointer doesn't exist outside this. Okay, now let's look. Comment this. This should work, yes. All right, that printed stuff. Um, yeah, that's another thing I want to share. Open thing. All right, so the first thing, so standard unique pointer, okay, makes unique, does all this. Now, first thing is when foo gets constructed, it prints foo. So that's what it did. So here the object, okay, you can think of it like a new foo was created or a standard make unique. Both are sort of they're basically the same thing. It creates an object. So a constructor of foo gets called. You can think of it like a class also instead of struct. Anything is fine. Either is fine. So now the important thing is because the constructor was called, okay, we do this also. Let's go step by step. The constructor was called, so foo gets printed. Now you might think there's a destructor also gets called because this is the destructor, and this line was also printed. That happens because if you see the scope of this SPTR goes auto scope here. Okay, so this is the important thing. Um, just a second. Yeah. Pointer goes out of scope. Okay, and who is destroyed? All right. So this is the important part where S pointer has only existence inside these two curly braces, right? Here it gets created, so that's why it prints foo because this is the part of the constructor. And then in this second one, when it goes out of scope, the destructor gets called, okay, and it gets deleted. Now, uh, this is another way, that's fine. Now we'll call this function. Okay, what this one does is it calls bar. All right. If S is not null, then we'll print it. So that's what we'll do. So foo polygon bar, which we have defined here, gets printed. That's fine. Now let's take things to a next another level. So we'll do this. Where go step by step. I'll create a few pointer, but this time I'll use standard move. So standard move is essentially think of it like whatever P owns is now moved to another Q, like that. Sorry, this is not P, my bad. Yeah. Okay. So essentially, this is basically the same type of pointer. Again, a unique pointer, a smart pointer, but now owns whatever S pointer was owning. So let's print this. Right. Again, prints all the time. That's fine because standard move has just moved. But this time we'll add another line. So we'll call the function f, which we defined here. So it takes a data type of foo reference and then prints this. So that's what we're passing. The Q pointer is a data type which has which is of data type foo, okay, and then prints it. It's not a copy, it's a move. Think of it like it's not another instance of it, okay, where there is different memory for uh, S pointer and Q pointer, okay. That's pointing to the same object, same memory. It's just that now before S pointer was uh, being pointing to something, now S pointer isn't pointing to it, okay. Q pointer is just pointing to it. So there's a difference between move and copy, okay. S pointer will move to that instant. We can actually check that. Probably yes. We can try printing this inside here. I think it should, but let's see. Oh, it did. Okay. Um, S pointer is still pointing to bar. That is fine. Okay. Let's. I want to cover uh, the other pointer also. So let's cover that also. Okay. Yeah, I get what you're saying. It for now it does. So yeah, it doesn't point to the null. It's like make it null, but at least think of it this way. It's not a copy in the sense it doesn't point. Q pointer is not like so. It doesn't make unique, right? So it creates an object instance of an object of data type foo, then stores a pointer. Q pointer with standard move essentially means I created another pointer which points to the same thing. In that sense, you can think that way. Okay, now let's do the other one where now this will print the f const. Oh, basically this function was called. Okay, now we move it back. Okay, and then destroy the. We destroyed q because q pointer automatically goes out of scope. The nice thing is q pointer, since it goes out of scope and is a smart pointer, it automatically happens. Okay, so let's say we do not remove this. Okay, we store it in S, right? And then F has it. Okay, that's fine. Then we don't move, destroy it, and then okay, before doing that, let's do it this way. So we should be saying destroys qptr, that's fine. We call bar again, so bar happened. Okay, but what if we don't move? We can try this out also. I hope this was clear. Q pointer was all its lifetime was inside this scope. So it did a RI here. Okay. And here it should print because we moved it back again. But what if we don't move? Yeah, that's the thing. So if you don't move, right? So S pointer becomes um, null because Q pointer was destroyed, and that was the object that Q pointer was pointing to, which originally was pointing to by S pointer. Because it gets destroyed, now S pointer is just null. Okay, all right. So this takes care of that, this condition. And then automatically S pointer itself, which again is null, but that's fine, goes out of scope here and gets destroyed. So if you see a lot of this code, if I comment also, okay, the code doesn't break. As in, of course, there should be still some logic here, but what I'm trying to get at is smart pointers actually make memory management very, very easy. You can start writing code like this, and then automatically, where management of memory automatically happens. Okay, if I have this, then now foo gets printed after destroying qptl. Okay, all right. Awesome. Any questions so far? Yeah, you can. Smart pointers are here to save you from that. Okay, let's include your screen. Good. Memory. Yeah, if you're not careful, then yes. But that's what sometimes people just want things to automatically take care of itself in a way. Smart pointers do provide a method to that. So we'll have shared pointers now. So this was unique pointers. Okay. Now we'll have shared pointers. Main difference between, I think it's a good time to explain. The main difference is that unique pointers only make sure that a specific instance has access to that object. A shared pointer means many pointers can have access to that same object. Okay, we will see some example. some shared pointer integer p, let's say. Okay. So we'll make standard make share. Okay. Again, we'll use the newer syntax for this. Make shared text template function done. Returns a uh, unique pointer, sorry, a shared pointer and stores in P. That's it. Compile time, yes, because these are templatized, so they are compile time. Runtime also true because when things go out of scope, RRID happens. So yeah, it's sort of a mix. Yes. The RRI happens also during runtime. Okay. Yeah. As in the acquisition happens during runtime. True. The destruction also happens during runtime. Let's say I store. This is basically an integer pointer if you think about it. I've written a lot of stuff, but basically it's an integer pointer, right? So I can store dereference that pointer, store value 3 to it. That's fine. And then layout. Okay. P done. Okay. And then P and END. So I'm printing P here, dereference it, and it prints 3. That's fine. We sort of understand what how to put it. This value will give you. There's a concept called reference count. So let's do that. See how. The first time, okay, this reference count is p dot use count. This function basically keeps track of how many references are coming to p. Okay, see the use now. Then standard set pointer integer. I'm defining another pointer now, q, which takes p itself. So whatever p was pointing to, and I stored 3 to it, q is another pointer pointing to it. Okay, same thing. The second time I call the reference count to q, also to p. Here I'll put q. So use count is basically a function defined for shared pointers, okay, which keeps track of something called a reference count. What's the reference count? It is essentially a number of times uh, same pointer is being pointed to. Now this is also again internally there is taken care of by shared pointers. So here I've created another shared pointer pointing to same p, like pointing to the same object, whatever p was pointing to. And now we can print and see reference counts. Okay. So let's compile and print this. The first time p is printing, that's time. That's the value we stored, it prints. And the next line, use count, it says 1 because only one pointer is pointing to that object. Okay. And the second time, I created another pointer q. So this one shows 2 because q is pointing to the same object, p is also pointing to the same object. From reference count perspective for q or p, they should be the same, as in they're both 2. Okay, because they're both pointing to the same object. The two pointers pointing to the same object, q itself keeps track of it, p also keeps track of it. Okay. You can do something called a reset. Okay. And then see out. How many pointers are pointing to the same object? Not how many pointers are pointing to another pointer, more like how many pointers are pointing to the same object? This time, okay, I just copied. So same P now, okay, I'll reset. So let's see the instance. It is 0, which means there is a function reset. Oh, sorry, I should not call it 2 and call it 3 and repeat. My bad. So we see it as 0. What this one function does is it resets all the pointers pointing to that object. So 0, as in no um, pointer is pointing to that object anymore. Okay. Can also do this where you do a p dot reset, but this time set it a new pointer. Yeah, it makes it null. Anyway, I mean it actually sort of like yeah, it makes it null because p is still existing. It makes it null. While resetting, you can also actually try to do this. Initialize a new integer or new object. So using the integer, in a way, think of it like class, new number with 11. Okay. So now P has a reference count. Okay? We'll try to print the reference count. And also we can print the value. I'll put it. Oh, yeah, that's it. Let's print this. So all this was, I think till here it's fine. So reference count is a reset, that's fine. But while the second time when I reset for uh, instance like this 4 and all, I create another pointer with new with value 11 as an integer, and whatever that new pointer gets created, that is the new resetted value for P. So the reference count now sets to 1 because only one pointer is pointing to that object. Okay, that's what this one prints. And the value, if you try to print with dereferencing, okay, it prints 11. Okay. Now let's say I set P to null pointer. Then if I try to print, I can use this same thing. I make it a fifth number, use reference count. Okay. Let's say I have this also, but commented for now. Let's so why not return 0? Yeah. I make it a null pointer. When the reference count still again goes back to 0. Okay. All right. If I try to dereference it, I guess you can expect what happened. It's a set point. Okay. So these are smart pointers, where another instance is used to use shared pointers. Here we use unique pointers. Okay. Take one last example. Yeah, I guess that's also fine. Any questions? Awesome. Okay. Yeah. Yes. Smart pointers are also not very complicated, as in once you understand how they work. So we started with this, and then we basically made a wrapper class. Then, because STL just provides it, we just see the different use cases for how to use the smart pointers. So this is one example, and then you can also use shared pointers, and they have some functionality called reference counts. Okay, so use count basically keeps track of them. So funny thing, I was in fun fact. This is how actually using reference count is how Python keeps track of memory. So you might have seen you can write. I don't know if you guys know Python, but anyway, let's say we have some variable p. So you have some variable a. Let's say it has some memory, and you have maybe made a list or something. You can set b equals to a. You can set c equals to a, b, and so on. Then what happens is out when something like this happens, you're basically making a copy or move or whatever. Internally, Python also keeps a reference count to that object. Okay. When reference count goes to 0, okay, then it frees that object, as in deletes that object. Sort of very similar idea, like what we are also doing here, as in both have the same idea. That's what a reference count is. In shared pointers, when reference count goes to 0, okay, then the actual deletion happens. Point to that object. Okay. So let's say I had Q, I had P, and let's say I make such that Q goes out of scope here itself. But still, since P has a pointer to that object, the actual object still stays. I mean, it doesn't get deleted. Okay, like that. And when finally Q gets deleted, P also gets deleted, the actual object gets deleted. As in, then the reference count goes to 0. That's how memory management works in shared pointers and also in Python. Okay, but we can't control that, right? Like here we have so many controls to work with. Controls as in Python, right? So I still don't get in C++, what is yeah, you have. Yes, that's true. In Python, you do not strongly type variables, but in C++ you do. So because of that strictness in a way, which is built into the language, you have a lot of control over it. Yeah, in a way. Mm. Yeah, in Python, you can't control memory. There are essentially no pointers in Python. Mm. Yeah. In a way, yes. It's a, I do encourage people to learn when starting with programming, learn programming first, then worry about language later. As in, when you're starting to learn programming, there is a flow to the algorithm. First, understand that. Write pseudocode, maybe write actually in a program. First, you understand pseudocode, then you write it into a program, let's say in Python. Then, when you see the actual your flow get executed, then you get more confidence as to, then you're more interested in learning the program, as in the language. Because you can write the same code in many languages and pretty much they will all do the same thing. Yes. But how they internally handle things is different. So Python will do things in its own way. C++ will do its own way, like that. As in every language will have its own way of doing things. That's when you can move from learning the programming to learning the language. Okay. It's difficult because every language evolved for a very specific use case. So having a single language for everything will uh, just think of it this way. Certain languages were developed for certain specific use case, like let's say front-end development. Um, Backend, I guess it makes sense to have very, I'm not entirely familiar with this, but just an example. Maybe there are certain parts of the code where you want speed or something. So you use some strongly typed language like C++ or whatever. But in front end, maybe where you want things to um, develop fast, okay, and you don't have to worry about too much bloat of code, as in too many lines of code. So another front end kind of thing happens. So like that, as in you don't always worry about same language being everything, because then the problem happens is the language itself becomes too bloated as to how many things can a language support, right? So hence you do hence there are so many languages, right? So each has its own pros and cons, and depending on the task you are performing, you use the appropriate language. Like Java is also very nice because the main reason to use is it is fast, yes. The second thing is once you compile it, and it always runs in something called a JVM. It's a Java virtual machine. So the good thing is once you compile it, you know it will run in any kind of environment because it has to always run in a JVM. Um, C++ works a little differently, but sort of the same idea. Yeah, in a way, machine independent. But the problem is, let's say I compile my C++ code in some instructions which are very specific to this CPU, this generation of CPU. It might not work in another CPU, another system with another different kind of instruction. And let's say that instruction is not there in that CPU. So you have to actually compile it again. So there are very specific cases where this cross portability or this portability will fail. But let's say in most cases, it will still also work. If you dynamically link your compiled program, you can still use the same executable, okay, in C++, uh, built in into Java. So that's something, maybe if it's important to the developer or user, then they'll use that specific language in that sense. Yeah, it's rare. Yes. Again, depends on use cases. So yeah, I wouldn't say it's rare. I guess people who use it, no, they'll say it's not rare because we are using it. So who knows? Okay. Um, you can look at online resources. I'm not sure where you can get specific questions, but maybe I'm sure there will be online resources. You can actually take look at the documentation of smart pointers in CPP reference. They'll have some examples. You can look at that. Yeah, I mean, honestly, smart pointers is all about using the syntax correctly. Again, it depends if how much you're working with pointers. So then it will make more sense. Yes, you can think of code on the fly and just try out few things to understand better. That's also fine. Other than that, you can definitely find online resources. As in, I'm not sure which one to refer to, but yeah, maybe just Google smart pointers and then some top results can point to. Oh yes, yeah. If you are in working with C++, C, or um, languages like this, pointers will always be there. Yeah. And honestly, this is a very, I at least think this is a very neat way of handling pointers where automatic destruction happens, acquisition takes care of things, and I think this is very nice. So while you don't have to then worry about where things are getting destroyed and all, right? So when you pass around pointers, you can just pass around smart pointers. And then if it's unique, it's unique. If it's shared, then reference count keeps happening. So yeah, yeah, it's been fun to uh, teach you guys. So yeah, thank you so much. I do like it when people actually enjoy the course. So thank you. It's a uh, helpful feedback to have. It, I do teach this as part of TA-ship, sure, but in the process of it, if people are learning and actually enjoying the this session also, so that makes it all the more better. So thank you. Thanks so much. Yeah, and again, before I guess ending the session, advice is the same. Practice more, as in write the code, like actually write the code and run it, which will take you through the process of actually compiling it. So if you have made any mistakes in syntax and all, the compiler will throw errors. So you actually then go in that process of debugging. And then let's say while running, you encounter errors. So what kind of errors those are? Are they seg faults, or are they give you some answers that you did not expect? But then why did it happen? Okay. So that's how you learn. The more you practice this way, the better you get at it. And with any new concept, be it lambda expressions, smart pointers, or whatever, any new concept that you're not familiar with it and let's say you want to learn in C++, especially, or any other language in a way, the more you write the code, that's more you get better at it. Yeah. So that's my suggestions. Yeah. The uh, overwhelming thing happens when you look at the full big picture and especially include the things that you are not yet familiar with. So again, the important thing is to take step by step. Maybe first learn this concept first and then move on to the next and so on and so forth. But also it is important to look back and look at the whole, all the concept that I've learned, okay, in a bird's eye view, then you actually get a bigger picture of the whole language. Doing that regularly will not be advisable, but I would say maybe do it in some maybe some time, like keep gaps and then do it. That will make you appreciate the language more, and then also tell you how much you have progressed, as in how much you have learned, like all the things I've learned. Uh, but doing that frequently it might feel overwhelming because you might think, oh, I still have to learn so many things. I haven't only done this, so that's yeah. That will make you only feel overwhelmed. Yeah. Oh, again, like going to assembly level takes more getting used to it because mostly the programs that we write, these programs, they have a flow to it, as in there are concepts, but they're still limited to C++ general programming. They're not yet assembly level or something. Yeah. Uh, Again, compiler is a different beast altogether. So learning that requires a different steps in a way. Not always, honestly. Uh, you are, I mean, if you are interested, you can always learn to any level you want and go to any depth. But sometimes just to write programs, you do not need, when you're starting, right? You don't need to know how compilers work, honestly. But if it's something you're definitely interested in, then I would definitely encourage to go for it. Yes. Yeah. Yeah. No, that's the important thing, I guess. Staying curious. Um, Keeping the balance between staying curious and not getting overwhelmed also. So yeah. All right. Thank you. Thank you, everyone. I really hope you enjoyed the sessions, enjoyed the course also. Yeah, thank you. I really hope it was fun. And yeah, until we meet next time, and happy coding. Yeah.